Hello. Hello, super prompt people such as Genesis who joined super promptly. Good afternoon, Yaneli with the double. And yes, good afternoon, Genesis. And I saw you when I was in the other meeting. Okay, yes. Sorry. Oh, sorry. Good afternoon, Natalie. My bad. Good afternoon. I don't know where there. Okay, now okay. I mean, I was getting a little nervous there. Okay. Good afternoon, Venita. I will not. I'm gonna be like Bart Simpson. I'm gonna write on the board like 100 times. I will not rabbit hole about Pokemon today. I will not rabbit hole about Pokemon today. I will not Pokemon about Rabbiton today. Okay. Um, Mario and rabbits. Um, good afternoon. Good afternoon, Carlos. Good afternoon, Sydney, with the exclamation point. Thank you for the enthusiasm. So now I'm ready to go. Good afternoon, Brian. Okay. Okay. Um, so here we yeah, okay. So here we go. Welcome back, everybody who wasn't here on Monday. All right. We get through this class and then you have a break, or at least from me. No, you still probably have 2.5 more days before. Okay, so all right, we're gonna do something sort of thick today. Um, okay, I'm gonna make some quick announcements. Wait, here, let's go. Where's the board? Where's the board? There we go. Okay. Um, Sorry. And good afternoon, Gabriella, and good afternoon, Chastity, both of you with the exclamation points, and Sydney. Between the three of them, there's so much enthusiasm in the room. How could I do anything but deliver an enormous amount of physics in the next 75 minutes? I appreciate the punctuation marks and there's going to be a new portal for punctuation marks. No, there's not. Okay. No, yes, I'm ready to go. We're excited. We are excited. What we have to do, so we're about to do a a thick computation today. We're going to do it from beginning to end, and it's from a homework. Um, and once we get rolling, there'll be, I mean, I'll definitely want to answer questions while I go for sure. But I know from experience and from the last class that we will exactly do this one problem today and we'll finish it like right, as the class period finishes. So therefore, let me get a couple of quick reminders out before it commences. Some of this I may have said before, just to reinforce. So it's that time of the semester where, of course, we're all getting tired, we're all overwhelmed, and maybe some of us are getting nervous about the end or about grades or things like that. So let me just again say to you, I always fall apart at this point in the semester. I'm totally behind. You are ahead of me. That is a better place to be than the alternative, even if it causes you anxiety. And I apologize, i.e., I am going to try to catch up over the break, and first and foremost, finish your exams and get your exams back to you. That's the goal. That's the hope. That's the goal, and that's the hope. But in the same spirit, just to remind you, if you and I hope that you take a break over break. In fact, before I go any further, somebody pointed out in the other section, I almost forgot. Somebody put the other section that I may have inadvertently assigned a homework to you for the middle of break. Or no, or was that the other class? Wait, let me just check. I don't mean for you to have homework due in the middle of the break. So I'm just quickly checking right now if I did that by accident. Did I do that? No, no, that was the other class. Okay, I think you're set. You should not. Is that correct? Yeah, yeah. Your homework is due. I'm so confused. Well, your homework is due the day you get back from break. That's not ideal either. Actually, I'm going to change that right now. In fact, And it's a big, I'm gonna warn you right now. Okay, wait, so wait, today is the ninth, so you break then, so you get back. Um, all right, I'm extending it. I don't mean for it to be the day you get back. Right now, I'm changing it right now, so it's the Wednesday. Even that might be, you might need a little more time that we'll discuss, but okay. I just changed it right now. So your next homework is, and it's the last homework in this class. I'm changing it in the other class too. It's so you should not have anything new to do during break. That's the intention. Um, it means, and the reason I'm saying this, sorry, let me just fix it in the other. The reason I'm saying this is if by chance you're trying to do any kind of catch up during break, or or you're nervous because you haven't gotten your grades back yet from me, if you're looking to um catch up on material or points, right? If during the break you're just like, oh my God, I'm getting desperate. Is there any more points that I can get in this class? Like while I'm waiting for my exam score or something. I totally understand that. I respect that. I'll be doing something similar for you during break. So if you're in that mindset where you're like looking for gaps that you can close or something, um, I recommend two things. Number one, go backwards, not forwards. That is, if there's some old homework that you still want to do, which you can, right? The portals are still open. If you didn't do it at all and you didn't hand it in on time, a first draft, then you won't get all the points for it, but you could still get enough points to be worth it. But if you're going to do that, if you're going to do old homeworks that you never did, go backwards. Look at the most recent thing first, eh, because it'll be the most helpful for you to feel caught up in what we're doing right now. And it'll be the most helpful for you for the final. Like, go to the most recent first, okay? And then if you're totally lost because you're like, I haven't been paying attention for 3 months or whatever, okay, then, go back from there and see what you need to do to figure it out. But go backwards is my first point. If you're trying to do anything to catch up or bring yourself back up to speed in this class, that, okay. And then number two, a similar note, if you're triaging, as I always am, if you know what I mean, um, if you're looking for just like to get more points or just, as I say, just like close gaps and fill in holes just to optimize your situation in the class as we get to the end of the semester, if you look back at any old assignment that you ever did, um, and you did on time and you got a bunch of points, but you didn't get all the points, you're welcome to look back at those assignments and see if there's anything you can do to get more points. I mean, if you're like looking for kind of like low hanging fruit or things, I hope you understand what I'm saying. This is all just if, right? If you're looking at old assignments to try to get more points on them, which isn't the worst idea, even if there's some old assignment you find that you didn't get a perfect score, but you still never got feedback on it, which is possible, um, just look at it. And again, go from most recent to least recent. Look at it. And if now you look at it now that time has passed and there's been more material, if you can look at it and see, oh, yeah, I remember I never even did the last problem of this assignment. Like I handed in a partial thing to get some points. But now I could do the last problem because he's like subsequently talked about it, or there's a video about it, or whatever. And or you look at it and you're like, oh yeah, okay, even though he never told me, I totally knew that I didn't know what I was doing. Yeah, I know what I'm doing now because he's lectured about it. If you see what to do on an old assignment to get more points, by all means, save yourself a step and save me a step and just hand in a revision based on what you've learned since then. And it will automatically notify me, it'll alert me, and it will sort of bring you to the top of the pile. It's just a faster way for both you and me to triage and get you more points or more, okay? Or if corresponding, I mean, conversely, if you see an old recent assignment where you got a bunch of points, but you didn't get all the points and you didn't get the feedback, and you look at it and you're like, yeah, I don't really know why I didn't get all the points. Honestly, like I'm looking at this, I did everything. It looks complete to me. I don't know why he didn't give me all the points. So then or I know it's not complete, but I really just don't know what I was supposed to do. Like I got as far as I could with it, and I'm like waiting for help on this. Then just write in the portal. I mean, just write me a note and say, could you take another look at this assignment? It's still missing points, and I'm interested in getting all the points, and I don't know how or why. Just send me that. Similarly, it'll send it to the top of the pile for me, and it'll alert me that you and I are trying to close gaps for you in the most efficient way possible. So do that, and then I'll either send you feedback like essentially right away, faster, or I'll be like, oh, you're totally right. I'm so sorry. I'm getting you. Actually, I just owe you points at this point, and I'll give you the points. Okay. None of that. Oh, okay. So none of that is a command. That is just like if you're in that mode of trying to close gaps while you wait for further grades, um, be my guest to do it that way. Or if you're trying to catch up on material to learn for the end of the course. Okay. So Annie, sorry, yeah, Annie.
Yes. So I have a question on like the score like weighing. So I know that we can earn like points from doing homework and also from like the game portals. I was wondering if the points are like the same, like if they weigh the same, like
Oh,
7 points from game is the same as like bringing like my homework score up by 7 points.
yeah, that's a very fair question, and there's a very direct answer. The answer is yes. For good or for bad, yes. Any point, this is true for all of you. Okay, I mean, it's good to worry about. I mean, good to know. Yes, and it's not supposed to be a secret. I mean, I know the grading system is like unusual, but all of this, it does say in this, like, it's in the syllabus. But yes, yes, yes. The answer is every single point you ever get, any of you ever gets on anything that is not an exam, all of those points are worth the same. Yes. Now they do all get divided. Like they're not worth the same as an exam point. I mean, to be clear, right? They're all getting, but they are all worth the same as each other. Yes. I mean, that's the simplest thing I could. So yeah. So you literally, I honestly, if the secret implication behind Annie's question, I mean, it's not a secret, but if that means any of you, if you're sitting down and you're like, wait, I could like redo this thing for 8 more points, or I could like turn in 2 more times that I showed video that I have the screenshots for. Like, yeah, turn in 2 more times that you have video. Like, absolutely. Yes, yes. Okay. So hopefully that is that. All right. Do you want to, is there another question, or is that the hand for?
Yeah, so when you said like, oh, I have like submit the screenshot of one time you like showed video. Like what if I have the screenshot but it's from like say like a week ago and I just didn't submit to portal. Like can I still do it?
Yeah. No,
Okay.
that's right. And that's kind of why I'm giving this whole speech. Yes, yes, to all of you. Yes. Like, yes. I mean, the simplest answer is yes. Now again, with something like that, with like showing okay, let me be super clear. Only thing I don't want, there's 2 things I don't want. What you cannot do, any of you, you can't the 5 point, the regular everyday 5 point game turn thing, which even that I've even fallen behind on now, and I'm like totally embarrassed by that. But they're all there, and they're all stamped, time stamped, and they all will get the points. That daily game turn for 5 points. That don't go back and retro those. It doesn't make sense. That's meant to be a daily reflection thing. Don't go back and retro those. But anything else, all of the other game portals, and you could tell the difference because those are every day, and all the others just have one due date, which is like the end of the semester. So that's the reason for that. All of the others, anything that you find or remember, even if it goes back to February or something, absolutely you can retro it. And that's why it's good to have like screenshots or something. I mean, if you have a screenshot that you showed video last week, yeah, by all means, put it up. Just writing to me a note, whatever. No, I'll leave it at that. So yeah, that the only other thing I don't, well, we'll get to this. The only other thing I don't want, and maybe this is also why I'm making this little speech before break, is what I don't, all the past homeworks and catching up and loose ends, all that's due the last day of classes. And then, as the final boundary. And then after that, it's all about the final exam. So to all of you, the other thing I don't want or I won't accept, like on the last day of classes, don't suddenly submit a huge pile of a bajillion game things and worse, like homework one, homework two, homework three, homework four, all done from scratch for the first time, all in one big pile. Don't do that. It's because, well, for 1,000 reasons, but honestly, I think we all know and of course it happens every semester. Like and to give the classic exaggerated version of why that's bad, like before COVID and before all this was electronic, the last day of classes in my office door, I used to get there would always be invariably like be one or two students. They would put a stack of all of the homeworks, all stapled together, like under my door in the office, all together, all at one time, all on the last night, and all like literally in identical handwriting, like all throughout, like with no scratch outs, no cross outs, no thinking, like just like perfect one handwriting, one pen color, all throughout the whole thing. And you know what I'm saying? Like, obviously, that person did not do all that. I mean, they obviously just sat down and copied it all from somebody else. Like, and that's ludicrous. And it's like, it's insulting to my intelligence. And you get what I'm not saying this to Annie. I mean, I'm saying it to any, I'm just saying, don't be preposterous. I still want you guys, I'm late, you're late. Like, you can go back and still do things, but don't be ridiculous about it and try to start doing it now. Don't right on the very last day, just give me the entire course as one packet that you got from your friend, because that's just like not doing either one of us any good. Okay, but you all get that, I'm sure. So, okay. All right, so any other? So I'm about to like do like a major physics problem. Well, oh, all of this is to say the problem that I'm about to do from start to finish is the part B of homework 6. Like last class, we did part A, and part A was kind of exercisey and was ultimately trying to come to the conclusion of what an electrostatic field is. An electrostatic field is an electrostatic force per charge. I'm going to elaborate on that in a moment. But that was the conclusion of Monday's class. And it was the end of a series of exercises that are exercisey that constituted part A of homework 6. Now we're going to use that conclusion to walk through part B of homework 6. And it is a thick computation. I'm telling you right now. I mean, once I start, it's going to be the rest of the class to do this one big thick computation that is part B of homework 6. And it's numerical and the numbers are not pretty. I mean, I actually they sort of start pretty and they're meant to be pretty, but they end up being like disaster. The numbers end up being very messy, and I feel bad about that, but that's just the way it is. I mean, hello, that's nature sometimes. So like once we get into the thick of it, I'm going to ask you to just like follow along with me. I mean, of course, ask questions, but but it is a problem worth knowing, and it is often on the final exam, and blah blah blah. And so, long story short, if you did already, well, I'll look right now. I mean, because I know this is that time of the semester where we all fall behind, and it all gets harder and harder to stay on top. So I'm looking right now. I'm not going to mention names today, but like homework 6 is what I'm talking about. Okay, homework 6, the part B is what we're about to go over. Out of 24 of you, 13 of you have already turned it in on time. Thank you. Noted. I'm not going to mention names, but I see who you are. That 13 of you have turned it in, and that's great. And that means that you turned in something, you turned it on time. So now, even if you found it to be a difficult problem or you find out that you made errors, of course, this would be a good example of anything over break. If you want to correct and resubmit based on what I'm about to do in this class right now, like good idea, I would recommend. I because again, this is a problem that will appear on the final. I mean, even if there's choices, like it generally is a big piece of the final. Okay, but the other 11 of you, I understand you haven't turned it in yet. Like, I get it. We're at that time of the semester. Uh, because you haven't turned it in yet, like you can't get all the points, but I assure you that if you benefit from the instruction that I'm about to try to give you, if you pay attention to this class, you'll be able to do this homework 6, and you'll still get definitely most of the points. You'll get enough to make it worth your while to do the practice and hand it in. Okay, so that, of course, it's the same system as always. I'm just reminding you because it's that time of the semester. So, what I'm about to do, yeah, what I'm about to do is a quick screen share. I'm reminding you what I'm just looking at the. Oh, and sorry, and I didn't say. Did I say good afternoon, chat? Oh yeah, and Emanuela, good afternoon. Sorry, I didn't say. So I'm gonna do what I'm talking about. What I'm talking about is this. Did it do it? Yeah. Okay. So I'm talking about now this problem that we're gonna go over. Okay, I'm gonna just briefly so the setup so we're gonna do the whole thing. The setup is that somewhere in a Cartesian plane coordinate system in the lab, we have in the lab, we have a source, a point source charge, much like we were saying on Monday, right? Monday was like 50 coulombs of positive charge sitting over here. Today it's 5 coulombs of positive charge sitting over here at the coordinates 5 comma 4. Okay. But over then here at the coordinates 10 comma 3, we have a point charge of -2. So in short, we have like 80 quintillion protons jammed together over here at this spot. And then we have like, 40, like 32 quintillion electrons sitting over here at this spot in the lab, okay, jammed together. And then at 0 comma 0 at the origin of this coordinate system, we've just decided to focus at that location, and we've got we've got a chamber there, kind of like we had a chamber yesterday, but what actually, instead of a chamber to put something in, actually now it even says we have like a field detector. We have a little measurement equipment at the origin of this coordinate system at 0 comma 0. And what we're going to try to find, well, our measurement, we're going to try to measure the electrostatic field that we find at that point at 0 comma 0. We're going to measure the electrostatic field that exists due to the presence of this pair of point sources. Together, these point sources are making an electrostatic field like everywhere in the world, and we're measuring the magnitude and the direction of that field here at the location 0 comma 0. Like, and I keep saying measure. Like if you're picturing this in the lab, then you would picture us measuring the field magnitude and direction at the point in space 0 comma 0. Now here we're doing it as a homework problem. We're not like literally using equipment. We're going to analyze and compute. We're going to figure out, we're going to determine what measurement we would find for the electrostatic field at the origin due to this pair of point sources, right? That's what this problem is about. It is about what is the electrostatic field at a given location due to two TWO point sources. That's what the problem's about. I mean, that's what the problem is. Uh, First of all, just like typographically, if you look at the problem here on the screen, it's not meant to be confused. Again, if you're going to go back and do it after this lecture or whatever, it's not meant to be confusing. That 4/3, that's just a whiteout situation that got weird. Like it's not meant to be the fraction 4/3. It's meant to just say that the y coordinate for Q1 is 4, and the y coordinate for Q2 is 3. Okay, it just looks funny by accident, but it always throws people off. Okay, so I apologize. That's number one. Number two, I mean, I'm going to switch the boards back obviously in a second and remind you of the equation that's relevant to all this. And of course, I'm going to work out the math and the pictures and all of that in a minute. But let me also just give you a big overview again, or one more statement about overview. Like the reason we did the exercises yesterday in the order that we did and the way that we did is because we're trying to show you Monday, we were trying to show you how we move in our minds from understanding of electrostatic force, which is what one charge does to another charge, and for which we have a specific equation that predicts the numbers. We move in our mind from electrostatic force to the notion of electrostatic field. Mathematically, is a very convenient and simple change in our minds. The field is the force per charge. So force is what one charge does to another charge. Field is what one charge does to space. And then a second charge comes along to that place in space and feels the force from the field, right? That's what we're saying now. We used to say proton pulls electron. Now, let me say that better. We used to, or you might have said, or you might have thought, proton pulls on an electron that's at a certain point in space. Now we say proton pulls on a point in space by making a field at the point in space. If electron comes to that point in space, then it experiences a force from that field. Okay, it's just a different way of thinking about it. The way of thinking about it now is that the information that determines the size and the direction of the force, all the information that determines the magnitude and direction of the force, all that information can be captured in an arrow, a vector arrow, that we consider in our minds to be already sitting at every and any point in space, whether or not other objects are sitting at those points in space to experience the arrows. So we believe now, or we say now, that the minute you put something like a source charge into space, it automatically deposits arrows. At every point in space, it puts an arrow, and the arrow is all of the information of how big that charge is, the information of where that charge is, bundled together and then multiplied by the electrostatic constant, bundled together and captured in a little arrow, and an arrow is sitting there at the point in space, at every point in space. And then when a next charge, a second charge, a test charge, a lowercase q2 comes along and finds itself at that location in space, then it will feel that the effects of the arrow. It will experience the number of newtons that the arrow represents. And more specifically, and then I'm done with this little overview, more specifically, the arrow that's sitting there at space represents the direction and the number of newtons that will be exerted onto each 1 coulomb of positive charge that could ever be found at that location. So the arrow that's sitting there before the charges come along is the force per charge, meaning it's all of the numbers, relevant numbers, except for the number of how many coulombs are actually coming along to experience this arrow. The arrow is how much of a force, will be exerted per each 1 coulomb of positive charge. So So literally what I'm saying, and then I believe there's a chat. I just heard I will get it in 1 second. But I'm trying to say, and you'll see this, I mean, I'll write it, but I'm trying to say that field is force per charge, literally like F divided by Q. So what that means in practicality is then once you put the charge there, then force will equal charge times field. The field is how many newtons will be exerted per each 1 coulomb. So if you find a charge there of 3 coulombs, you'll multiply the field magnitude by 3 because each one of the coulombs is getting all those newtons. So the total number of newtons that will be exerted would be 3 times those number of newtons and in whatever direction the arrow is pointing, assuming that what comes along is positive. And if what comes along is negative, then it'll be in the opposite direction of the arrows. That's what we're saying. So we're saying field is force per charge. Force is something a Q1 does to a Q2, like a capital Q does to a lowercase q, but field is what capital Q just does to space. And then if Q2 comes along, it experiences that field as a force. That's what, so, oh, sorry, and I'll get the chat and then we'll go. So what we're going to be looking for in this problem, we're in effect saying in this problem, and I will totally get, yeah, what we're saying in this problem is that capital Q1 is depositing arrows everywhere. I'll draw them, I'll show them to you. It's depositing arrows everywhere, including on the origin. It's depositing a little arrow going somewhere on that origin. Then Q2 is depositing arrows everywhere. One of those arrows lands on the origin. So there's an arrow on the origin from Q1 and an arrow on the origin from Q2. What we're going to try to do in effect in this problem is add the 2 arrows together and get the combined effect, the resultant field vector. We're going to get the field at 0, 0 that is resulting from or caused by capital Q1 and capital Q2. And just to be super clear, we're figuring out the field at 0, 0. We're figuring out the force waiting to happen at the location 0, 0, just because we just picked 0, 0 as the place that we're interested in. Like it's happening everywhere. There's a different arrow everywhere. We're just choosing to get the arrow at 0, 0. Whatever location we choose to measure the field, I like to call the location of interest. But many websites and textbooks and so forth will call it the field point. If you ever hear field point, it means the point of space at which you're measuring or predicting the field. It doesn't mean it's the only point that has field. It just means it's the point where you're measuring the field. And that's what we're going to do today is like, we're going to find out the field at the point 0, 0. Okay, Annie. Sorry.
Oh, so I have a question. Like, my question is like, let me think about how to put it. So when you say like Q1 and Q2 like deposit like arrows representing like the charge everywhere, and then when we combine the chart like the arrows, we get one vector that represents the magnetic field. Is that what you're saying?
Oh, the electrostatic field. But yes, that is what,
Oh
yeah,
yeah, sorry, electrostatic field.
yeah.
But when I think about field, I think about like you said, like arrows like depositing everywhere. Like I think of like a region on the coordinate or like an area. But why are we getting like one arrows only? Or are you saying it's because we selectively like pick which arrow we want
Oh,
to
wait. Oh, okay. No,
find?
no. Oh, sorry. No, wait. That's a really good question. I think I understand it. I, okay, I'm going to switch the boards to show you my picture. But yeah, I am actively saying, I mean, yes, there's arrows everywhere. Once you say field, that means there's arrows everywhere for sure, like all different arrows everywhere. But I am specifically believing that at every point in space, once you pick a point in space, then at that point in space, there's one specific arrow from each one thing that's causing field. So like I am saying, so I'm going to show you the picture. I am deliberately saying that capital, or let me show you the picture of what I'm saying. I think those are, but yeah, I'm saying Q1 will put one arrow at every single point in space, for example, at 0, 0. And then Q2 will put one arrow one different arrow at every different point in space, but every point in space, it's like a function. Well, it literally is a vector valued function. In fact, quite literally, sorry, I'm not going to rabbit, literally field actually mathematically means vector valued function. So I am literally saying that that each point source, it makes a function. You name the point in space, and it will give you one arrow of a one magnitude in one direction for that one point in space that you named. But each Q1 and Q2 will do that. So I'll make this. So when we look at any given point, like the origin, we're going to see a arrow. We're not just choosing. We're literally going to only see one arrow that comes from Q1 and one arrow that comes from Q2 at that location. And we're adding them together to get the final one arrow at that location. So let me, oh, so I'm going to switch. So, I mean, it is a really important question. I mean, I think I do know what you mean, but I think I do mean like what I'm saying. Hold on. So yeah, okay. Oh wait, it's gonna switch. It's coming. It's coming. It's good. Yeah. So I mean, this picture is a little bit overwhelming, but but I believe that it's sort of addressing Annie's question. You know, obviously, it's not a. I mean, obviously, I didn't just draw it just because of Annie's question, but like I'm saying, go, if you focus your attention for a moment on Q1. Well, wait. All right. Well, first of all, let me just answer Andy's question. I mean, I'm saying that, yeah, a whole bunch of things are happening everywhere in space. Yes, it's like a whole bunch of arrows. But when you focus your attention, like on the origin or on any one point, you'll see a arrow at that point that's red from the Q1. And you'll see, although it's a little bit hard to see, you'll see a blue arrow. Um, at the origin from Q2. And that's it. Like not more than that everywhere, but not more than that at any given one location. I want to say a lot more about this picture, but in all honesty, because I think does that address what, I mean, does that address what you're asking, Annie?
Yeah, I think so. So basically, like the origin point experience is like um the arrows from both Q1 and Q2, like the charge arrows. But then we, for the homework question, like we got one vector for E1 plus 2, E sub 1 plus 2, because we selectively like look at the origin point, and that's why we got one vector.
Yes, as long as you and I are both agree, like, yes, as long as we're both agreeing that, yes, we selectively chose the origin to study, and that was just our choice. We could have chosen any point we wanted, and whatever point we wanted, we would have gotten different answers, but no matter where we looked, there would only be two arrows. Any point we would choose, there would literally be exactly two arrows there. But because there's 2 point sources, Q1 and Q2, there would be two arrows at any point we choose, and we would be adding them together to get one. And that one that we would get would be the field at that location due to the pair of sources, Q1 and Q2. Like, are we both agree? In other words, right? Does that make, I mean, do we,
Yeah, I think I understand it now. Thank you.
okay. All right. Okay. Thank you. Okay. So, sorry, I'm going to switch it. So, I'm just switching the, okay. So let's all focus. So this is my setup. I mean, for one thing, like if you're doing the homework and you're doing like step one DFP, I mean, it could involve almost as much as this. I mean, but I'm also doing this like to explain things. Like, oh, first of all, let me go backwards. First of all, notice the equations at the bottom. That's a summary of what I was just saying in English. Like at the bottom, I'm saying all the analysis we're about to do, like it starts with the force equation between two objects, Q1 and Q2. But the belief, the new way of thinking is if 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 in general, like 1 point charge will exert an electrostatic force on any other 1 point charge. But then what we sort of convinced ourselves Monday is that, you know, you it, is that it's really convenient and ultimately correct, I think, to look at basically, I'm just trying to say the top equation says force. It says what one object does to the other. But then the second equation right underneath it is field. Notice it's exactly the same equation. It just divided out by a Q2. Like it's just saying the bottom equation is just saying that the definition that E is the net electric force divided by Q2. It's lit. So if force is in newtons, then field is in newtons per coulomb. That, I mean, mathematically, it's not meant to be harder. It's actually meant to be easier. Um, Force is what one charge does to another charge, and field is just what one charge does. It's all the information of it's you notice the second equation is everything that the first equation has except the information of what kind of what how big of a charge is coming along to experience this force. And so we're just saying if all the rest of the information is ready to go in an arrow sitting there at a point in space, then when a charge comes along, once we know how big it is, we just multiply how big it is by all that field information, and we'll immediately know the force being experienced by the lowercase q, the test charge, right? So everything we're about to figure out in this problem is based on the second equation. We're about to compute the field occurring at the origin due to the contributing sources of capital Q1 and capital Q2. Now let's look at them individually for a second. What I'm trying to say, to everybody is if you just look at Q1, the moment Q1 started to exist in the lab, the moment Q1, this bundle of protons, was sitting there at that location 5,4, like it immediately put arrows everywhere in space and I just drew a bunch of them, just enough to show you the pattern. Like there's arrows everywhere. There should be red arrows everywhere, but of course I can't draw every. So I'm drawing enough to show you the pattern. And what is the pattern? The pattern is that first of all the red arrows being created by capital Q1, they're all pointing out. They're all pushing out away from Q1. Why? Because each one of those arrows is representing the force per charge, the force that's waiting to occur on each and every positive 1 coulomb of charge that could ever be at any location that the picture that we're looking at. So it's a prediction, if you like, of what would happen to a positive. It's always field is always a prediction or a calculation, whatever, of what would happen at a given point in space to a positive point charge that might be located at that point in space. So a positive source would always push on a positive test. A positive source would always push on a positive receiver. So all of those arrows that come out of positive sources are always going out. Like that's like a rule. You can remember, like it's always true. But also, so that's in terms of direction. They're going out along radial lines. But then look at magnitude. Notice that each one of the arrows is getting shorter and shorter as it gets farther and farther away, right? Not a coincidence, because r squared in the denominator, because r is in the denominator and then it's squared. The farther away you are from the Q1, the less you will be pushed by Q1. So it's trying to say, I mean, really, again, I can't emphasize enough what a field really is mathematically is a vector valued function. It's a function. The input is point in space. The output is a vector whose magnitude is newtons per coulomb and whose direction is either a push or a pull away from the thing that caused it or toward the thing that caused it. So any point in space you pick, there's an arrow sitting there telling you how each of the coulombs that you might be how hard and in what direction they would be pushed or pulled. Okay. So the field vectors from, and they go on forever. I'm just like drawing a slice of it. The field vectors from a positive always go out and they get smaller and smaller and smaller. But then notice over there the Q2, which is a negative 2 coulombs, right? Well, there the arrows, first of all, are all pointing in. And that's a rule. Like that's not a coincidence because Q2 is a negative and always, no matter what, in other words, the source of a field could be positive or negative. But what we're always imagining when we ask what field is, when we say force per charge, we're always tacitly, conventionally saying force per positive 1 coulomb charge. So all those arrows are a prediction of what a negative source would do to a positive test. The test is always positive, but the source could be anything, positive or negative. So sources always pull in. Excuse me, negative sources always pull in. So the arrows coming into the Q2 are going in. Also notice though, even though I didn't draw perfectly to scale by a long shot, notice that those arrows are all like even the ones that are even the starting arrows right closest to the dot, they're all a lot shorter than the red arrows. Why? Because technically they should be 40% as long. Every single one of those arrows should be 40% as long as its corresponding arrow in the other picture because Q2 is only a magnitude of 2 coulombs, whereas Q1 is a magnitude of 5 coulombs, right? 2 is 40% of 5. So those arrows are shorter and they get shorter and shorter as you go out according to the pattern, but they are like begin even shorter. You follow what I'm saying? So, yeah, so sorry. So each one of these point sources is depositing a bunch of arrows in the world. Each one of the arrows is a technically called a contribution to the field. The field that results is just that, is the field that results from all the arrows that are being placed everywhere by anything. The field is the result of all the arrows being added together at every point in space. So each object in space makes a contribution to the field. It contributes to every point in space its own singular arrow. Okay. So then when you this is happening everywhere, but we've decided to focus on the origin and ask what the field is at the origin. So at the origin, you notice there's a red arrow coming from the Q1. And notice, this is not a perfect drawing, but it's not my worst either. The red arrow at the origin is like meant to be pushing out along the line that would connect the origin to the point Q1, right? Like it's pointing along R1, so to speak, right? And then the blue arrow, there's like meant to be a blue arrow there at the origin. Make it a little bit clearer. It's pointing, it's hard to, you see that. It's pointing to the Q2, right? So it's at a slightly different angle and it's meant to be shorter, but that's, well, here. You know what I'm trying to do. I'm exaggerating now just to make a point. Just to try to make it a little bit clearer, right? So you've got an arrow from the Q1 and an arrow to Q2, and they're pointing at different angles and they're pointing in different directions and they're different lengths. And the whole goal of the whole problem, for which we now have 27 minutes to do, and we will, the whole problem now is just add those two arrows together and get the resulting vector E, the field at the origin. That's the goal of the whole problem. So now we're going to do that computation, and it's all based on this equation right here. We're adding the E from one to the E to the other to get the total E, but we're adding it as vectors. So we have to think of it as vectors. So if we zoom in on 0, 0, that's just the picture that I was putting it, right? We got E1, we got E2. So we got to add those two vectors. Well, now I'm going to, because now that we know what the vectors are, I mean, you want to hold in your mind what they mean, but now we're just going to treat them as vectors. We're going to do the same thing we would do to displacement vectors or velocity vectors or force vectors, anything else. So when you're adding vectors, you place, like, you make them tip to tail to see what the sum is, right? I mean, the first picture is a vivid picture of what's happening, but now if we want to start solving the problem, we place them tip to tail. So I zoomed in further, I sort of blew up the picture, and as you see, I just shifted the E2 down and placed its tail at the tip of the E1. And then I carefully, like, draw the line that completes the triangle, right? And that the arrow that completes the triangle, and that is the resulting vector that I'm looking for. Um, um, that resulting yellow vector, like that's the answer. And notice it, how do I know which way to make it point? Like, how did I know? Well, because I started its tail at the original tail of E1 and then made its tip go to the final tip of E2, if you know what I mean. Like I'm literally adding. I don't know how better to put that, but that's what you do always. So I didn't draw. So first note, if I had drawn this perfectly to scale, if I'd been careful with rulers and protractors, then literally that yellow arrow there, that would literally be our answer. Like if I did this with careful enough measurements, then you could measure the size of that yellow arrow and you could get a protractor and measure the angle, and whatever you got, that is literally the answer. Like if you understand, and the answer we're looking for, like that would be the electrostatic field at the origin. And that means the magnitude would be the number of newtons that would be exerted, that every 1 coulomb of test charge, if you, every 1 coulomb of positive charge that you could ever imagine being at the origin would experience that number of newtons, and it would be pulled or pushed by that many number of newtons in precisely that direction at that angle. Like, so if we, so like all vectors, we could actually get the answer graphically if we're careful enough with our measurements. Apparently, I am not careful enough with my measurements. So we want to do this analytically, and we will for the next 24 minutes. We'll get an exact answer. Well, we'll get a precise answer. One thing though, if I do my diagram vaguely well enough, which I did, it happens. Uh, then you can at least get a like a perspective on this, that you notice that that arrow points to the southwest. I mean, notice I'm calling everything to the right, I'm calling east, everything to the, and I'm calling positive, everything to the left, I'm calling negative and west, et cetera, et cetera. So notice my final answer seems to be pointing to the southwest. So if I trust my picture, then that means the final answer that I get at the end of this computation had better be pointing some kind of angle southwest. And if it's not, something's wrong somewhere. Maybe that, or maybe this picture. But I actually think this picture is okay. I think it makes sense. I like my intuition that I'm developing here before I do crunch numbers. I believe that field should point essentially southwest because the red arrow, the field contribution from Q1, like definitively points southwest, right? I mean, or pushes southwest, and it's a lot bigger than the arrow from Q2. Now, how did I know to make it bigger? I mean, was that a coincidence? Did I just randomly? No, I knew to make it bigger. It should be bigger. The red arrow should be a lot bigger than the blue arrow because remember, this is all coming from this equation, the bottom equation on the board, Q over R squared, right? Like Q1 is very big. It's 5 coulombs. Q2 is smaller. It's 2 coulombs, like magnitude. Also, Q1 is very close to the origin, and Q2 is farther away. So by either standard, like there's not even a conflict. The Q in the numerator is definitely bigger for the first charge, and the R in the denominator is definitely smaller for the first charge. So that first charge is creating a much bigger field at the origin. Like if I looked somewhere else, it might be a different story, but at the origin, it should be clear that the first contribution is a lot bigger than the second contribution. So therefore, I don't think that the E2, what it's going to do is make the field slightly less south and slightly less west, right? I mean, we're going to get a southwest angle that's less, you know what I'm saying? And we're going to get a vector that's smaller, I think. But we're still going to get a southwest vector because the E2 could only have just sort of lessened the impact of it wasn't big enough to win in a fight with the E1 on the x-axis or the y-axis. Okay, so anyway, so I think this picture is a pretty good picture. What we're solving for now for the next 21 minutes, what we're trying to get is the actual numbers, the size and the angle for the yellow vector E1. Okay, so how do we do that? We add to analytically add vectors, we add them by the component method. We break each one up into its x and y components and add the x and y components individually, right? Galileo's principle of relativity, right? The laws of physics are the same in each inertial reference frame coordinate system. So to analytically add the vectors and get a numerical answer for E, we resolve each vector into components and then we add the components independently. This is exactly what we did with velocity vectors, force vectors, displacement vectors. It's always easiest to picture with displacement vectors, but it's the same mathematical process with all vectors. That's why we spent so much time on vectors last. Okay. So that's what we're going to do. So I'm going to zoom in on the first vector on E1, the contribution from the first charge. Let me put that there. So what am I doing here? So I'm zooming in on E1 and I'm saying to be pushed to the southwest really means to be pushed somewhat south while simultaneously yet independently being pushed somewhat west, right? That's what's happening here. The southern component of your push is the push times sine of theta, and the western component of your push, E1x, is the push times cosine of theta, and theta is the angle between the tails of the two vectors, right? So I resolve, just doing the same thing I always did. I'm resolving the hypotenuse into a horizontal and a vertical, and I'm literally saying horizontal plus vertical equals resultant. So I'm literally making them tip to tail. I can't emphasize enough. I may already beat my brains to the ground on this in 203, but you can't just draw raw triangles. You have to put in tips and tails because it's all about direction. And in fact, I'm going to move on, but it's so much, the tips and tails are so much about, and you got to practice on your own because every time I draw a right triangle, what I'm telling you is it's the correct right triangle to draw. But until you practice on your own, you don't realize that it's just like many other right triangles that would occur to you to try. And you don't start realizing which one's better and which one's worse until you try them. It's anyway. You got to do this on your own. But look, what I am saying is the arrowheads are making the directions clear, and they're making them so clear that now I can just do the math of these triangles and just focus on the sides of these triangles. And I'm just now going to focus on pure magnitudes. I'm going to do math with pure magnitudes and then put the directions back in at the end based on these arrows. So E1x, if you're going to pay attention to any point in the class, I'm not looking at anybody. I'm just saying, if you're tuning in and out, this would be the time to tune in because I'm going to do the first component now out of 4. If you understand how I do this first one, all the other ones are the same. There's going to be 3 more of them that I'm going to do fast. So you want to understand this first one for sure. And then the rest will make sense to you. Okay. Okay, so get this and definitely stop me if you don't get what I'm about to do. I'm saying E1x, the horizontal component of the contribution from just the first charge. So the x component of just E1 is E1 times cosine theta. Okay, what's E1? Well, I'm using the equation and I'm just looking at magnitudes now. I'm not worrying about all the vector signs and all that. I'm just looking at magnitudes. So E1 equals that constant times Q1 over R1 squared. The constant, I'm rounding. I'm approximating, which you're welcome to do on any, just like you round gravity from 9.8 to 10. I'm taking that big constant. Oh, that's not written here. The big constant that's on the sheet, 8.9. That's you don't have to memorize, but you have to be familiar with it. The big universal electrostatic constant, the Coulomb constant, 8.99 times 10 to the ninth. I'm super rounding that so I could save time. And everybody does this when convenient, not in the lab. Never do this in the lab. Never do this if you're doing grant funded research. But like in an exercise, you can do it. I'm saying that 8.99 times 10 to the ninth. I'm rounding that to 9 times 10 to the ninth. And then I'm saying that's 9 billion. Freaking, let's call it 10 billion. It's a lot easier to work with. And it's a lot easier to work with. And it's not. So I'm calling it 1 times 10 to the 10th. That's what that number is. People get lost in this all the time. That's the K, that's the constant, okay? 1 times 10 to the 10th. That's the constant. Then Q is the Q of the first charge, 5, right? 5 coulombs. Then what's R squared? Well, what is R? R is the distance from the first charge. It's the distance, from the first charge to the origin, like that diagonal line, that hypotenuse. How do you get that distance? Well, you could say distance formula, or what is better known as the Pythagorean theorem, right? That's the hypotenuse of a right triangle that I sort of tried to put white like this triangle, right? That squared plus that squared equals this squared. And this squared is what the equation is asking for, R squared. So I put in 5 squared plus 4 squared is what R squared is. Stop me if you don't buy that. Again, if you do buy it, you're good because then the rest of this will be easy. But so that's E1 is 1 times 10 to the 10 times the charge divided by the hypotenuse squared. But then I multiplied it by cosine of theta. And the part that loses people a lot is, how did I do the cosine of theta? Well, I didn't. I did a trick. I didn't get theta and then get the cosine of that. I just realized that cosine of theta is adjacent over the hypotenuse of that triangle that I just showed you. What's adjacent? Adjacent is this, the 5. What's the hypotenuse? This, the square root of 5 squared plus 4 squared, right? So this, I'm saying, this loses people every time. I'm not saying that critically, but just be alert. This thing here is cosine of theta. Okay? So that, if I multiply out these numbers, which I will, these numbers make E1x, the horizontal component of the field contribution from the first charge. So I multiply out the numbers, right? Like the denominator is like 41, and then the square root of 41, same thing. So, 41 to the 1th power times 41 to the 1/2 power is 41 to the 3/2 power. I mean, it seems like obscure, but that's what it is. And it'll happen every time. So it's worth getting used to, right? So but these are just the numbers. So I work them all out and I get this huge number of 9, because these are huge charges, of 9.51 approximately times 10 to the 8th newtons per coulomb. Newtons per coulomb. This is a field contribution. What does this mean? This is not the answer. This is one of 4 pieces of key information that I need to get the answer. What is this? This is, if you were at the origin, if you look at the origin, that number that I just got is how many newtons of force each 1 coulomb of positive charge would be pushed to the left, like to the west, just due to Q1, right? It's the horizontal push due only to the first charge that each 1 coulomb of charge would experience if it's at the origin. And I keep saying would experience because I'm trying to emphasize there is no charge at the origin. The origin is just a location in space. We're saying that there's a number of newtons waiting at every point in space for each coulomb to come along and get it and receive it as a push. So the newtons per coulomb due to Q1 in just the westerly direction is that. Okay, now if you follow that, we have 11 minutes. It doesn't get harder from here, but it does get faster. If you follow that, in fact, I'm going to wait like 30 seconds. Like, tell me privately if even if you just like wait, I realize something really important just happened. I totally spaced out in the middle. Like, can you repeat? Like, this would be the moment to do it because from here on in, I'm just gonna. So, does anybody want to like stop me about anything about that? If not, does anybody want to give me a thumbs up to keep going? That's okay. That's good. Oh, and it was good. Fine. Two people. Great. Thank you both. I think it was public. So three. Great. Awesome. Thank you. Three. All right. So I'm going. So that's E1X. That's E1X. Sorry. That's E1X that we just got. Now we're going to get E1Y. Or we're just going to do the rest. E1Y. Same exact deal, only it's times sine of theta now rather than cosine of theta. Sine is opposite over hypotenuse, not adjacent. So I put in the 4 rather than the 5. That's the only thing I'm changing in the entire calculation, but it makes a different number, right? You see what I'm, so I'm saying, so I just did it, right? Same numbers, except for it's a 4 rather than 5. So I should be getting 80% of the other number. So now what we're saying so far is if you were at the origin, just due to Q1, you'd be pushed, every Coulomb would be pushed that amount to the west. Yeah, that amount to the west. And why am I saying west? Because look at the arrows, right? To the west. And that amount to the south. And I'm not putting negatives or positives. I'll put those at the end. I'm just saying magnitudes. I'm just saying something right now. So that amount to the south, every Coulomb would be, so it's newtons per Coulomb because it's a prediction of what would happen to every Coulomb. If 2 Coulombs were there, the total force would be 2 times this, et cetera, et cetera. So we got the horizontal component and the vertical component due to charge 1. Now we go to charge 2. Same deal, same method, but the numbers are different. The Coulomb constant again is 1 times 10 to the 10th, but now multiplied by the charge. The charge is now 2 rather than 5. Notice I'm just putting in the 2. I'm not saying -2. The negative. Oh, and I should make a diagram. What I did not do here that's sort of bad is this. If I zoom in, this now, right? This looks like this. Right? So this is now E2, E2X, right? I'm just lifting this from my other picture, E2Y. And notice that this time it's pulling to the northeast, right? Okay, so my arrows will explicate directions. I'm not putting negatives or positive signs into my side triangle computations. So it's 2 instead of 5 because the charge is different. And now the distance is again a hypotenuse. R x squared plus y squared. X is 10, y is 3. So 10 squared plus 3 squared is r squared. And then the cosine of the angle, adjacent over hypotenuse. The adjacent is 10, and the hypotenuse is square root of 10 squared plus 3 squared. Same pattern as before, just different numbers. So I work out the numbers and I get like 1.75 times 10 to the 8 newtons per Coulomb. So that's how hard the second charge is pulling to the east, right? The first charge was pushing to the west. This charge is pulling to the east. And then I do the final component, E2y, same numbers, but now it's the sine, not the cosine. So it's opposite over the same over the same hypotenuse. And the opposite is 3, not 10. I hope you see what I'm doing. And so I do out the numbers and I get the E2y equals that many newtons per Coulomb. Now notice that's a smaller number. It's 10 to the 7th, not 10 to the 8th um, uh, because the numbers are smaller. Okay, I mean, I'm just saying that's not an error. So we have 6 minutes. Oh, we could totally slow this down. We could just talk about Pokemon now for we're almost done. No, I'm kidding. But we are almost done. Um, So the question is, what do we do now? So the answer is we are now going to, the reason we did this is we can add, we're just trying to add two vectors together. But the whole premise is that you can only add that the X is one world of physics and the Y is the other world of physics. They're happening simultaneously, but they're happening independently. So we did this so we could divide things up into X and Y components. Well, now we're going to add up the X components and we're going to add up the Y components in an XY chart, just like we did with velocities and so forth in the midterm of Physics 203. Right? So I've got the X components of E1 and E2 and the Y components of E1 and E2, and I'm going to add them up. I'm adding them no matter what. But some of them are going to get minus signs. Like now I'm going to pay attention. Now that I'm literally going to do the addition, I'm going to pay attention to minus signs. E1 gets a minus sign on the X and on the Y because E1 is pointing to the west and to the south. It's pointing negatively on this axis. I mean, it didn't have to be, but it is pointing negatively on this axis and pointing negatively on that axis. So each of those components get negative signs in the chart. But E2 is pulling the other. I keep saying E1 is pushing and E2 is pulling. So I watch my negative signs, I do the math, I end up getting two negative components like we predicted. Like you see, the E2 did not have a huge, you see what I'm like, if you look at the numbers now, E2 just doesn't really, it's not big enough to change the directions of E1. It's big enough to chop some of the magnitude off, but not, you get what I'm saying, I think. So the answers I get after adding them is negative 7.76 times 10 to the 8 and negative 7.07 times 10 to the 8. So what do? Then I make one big triangle out of the X component and the Y component. Like this is the end of the day answer. And one thing, I'm saying, and I literally notice, and I always do vectors like this. I always draw my horizontal vector first. Whether I'm resolving a vector that I already have or I'm creating a new vector, I always draw the horizontal first. And I draw it in the direction that I'm told. Like if it's negative, I draw it to the west, right? That's what I'm doing here. And then from the tip of the horizontal vector, I begin the tail of the vertical vector, and I look, the sign of the vertical vector is negative, so that one goes down or south, right? It's all about being rigorous with the directions. So the west goes to the left, the south, the X one goes to the west, the Y goes to the south, and then the result that I'm looking for is the vector that points from the original tail to the final tip, right? And that vector points like unambiguously and deliberately west and south, i.e., southwest. And that yellow vector is the answer I'm looking for. And it is the yellow vector from the earlier page, right? And so when I do the Pythagorean theorem, I get the length of that vector, approximately 1.05 times 10 to the ninth newtons per coulomb. So that is the magnitude of the answer that I'm looking for. Like the magnitude of the field is approximately 1.05 times 10 to the ninth, newtons per coulomb. And the angle, the arctan of the opposite over the adjacent, the angle is approximately 43 degrees southwest as predicted. So that is my answer. Um, and that means, again, that means there's 1.05 times 10 to the ninth newtons waiting to push every single one positive coulomb of charge to the southwest, every one coulomb of charge that might ever find itself at the origin will be pushed this number of newtons to the southwest, right? And so if 2 coulombs of positive charge happen to be found at the origin, they'll be pushed with a force of 2.10 times 10 to the 10, like in other words, 2 times that, right? And if electrons happen to find themselves at the origin, then they'll be pulled or whatever to the northeast. You see what I'm saying? This is what will happen. The amount of force per each 1 coulomb of positive charge that might or might not ever be there. It's the force waiting to happen. It's called the field. And it's the answer to this whole homework problem. So, and it's 4:20. So have a great break. I mean, feel free to contact me with whatever, but have a great night and a great break. And don't do new homework, but talk about physics and Quark bless America. I will see you soon. Okay. Yes. Have a nice day.